Hi everyone and welcome to this new video. We continue with the subject of AC steady-state power analysis. This is our example number 3. In this case we have a different RC circuit compared to the example number 2. We have two resistors and one capacitor and one voltage source, which is shown here, and the values for those four parameters, for those four elements, are shown here. Again, as we have discussed in the two other examples, example 1 and example 2, about steady-state power analysis, we have four situations we have to calculate: the apparent power, the real power, and the reactive power, and the final is the power factor. As we did in the previous videos, we first sketched out what is the power diagram that will help us in the calculation of the unknowns, so power diagram. And since this is again a capacitive system, a capacitive load, I already know that the Q, so the reactive power, will be pointing in the negative y directions, or in the negative imaginary axis. So if I have the real power here, that's actually the P, and I will give in the green the Q, it will be minus JQ, and the vectorial sum of that will be the apparent power. Okay, this is actually a very important sketch, and we have also the phase between the apparent power and the real power, and we know that S is equal to P minus JQ. Now, we already know from the previous examples also it is important to determine the total impedance, which is actually R1 plus, and that was the difficult point, what is the combination of these two? So I will denote this as another impedance, so I will make a substitution for these two elements, R1 and C, and I will denote this as ZA. So ZA. So ZA will be placed here. So what is ZA? ZA is actually the parallel combination of the R2 and the XC. So I will also need to know the XC. So ZA is R2 in parallel with minus JXC. Because I don't know the XC yet, so let's calculate that. XC is equal to 1 over omega times C, and omega I already know is 1000, which is in the expression of the voltage source, and the 100 microfarads for the capacitor, which is 10 to minus 4, it's 10 to the power 4, 10 to the power minus 4, so I have the 1 over 10 to the power 3 times 10 to the power minus 4, which will result in 10 ohms. This is for XC. Now, let's move on with ZA. ZA is written in a different form as J times R2 times XC divided by R2 minus JXC. So substituting the values will be R2 is 40 minus J times 40 times 10 divided by 40 minus J 10. Okay, now if I rewrite this, now we'll have minus J400 divided by 40 minus J10. Now divide everything by 10 will reduce to minus 40 divided by 4 minus J. Okay, this expression can be written in different form by using the complex conjugate of this term. So what I will have is the following: ZA will be equal to minus J40 times 4 plus J, and then 4 minus J times 4 plus J. So that will result in a real part in this expression. So what we have is the following: will be 40 minus J160, so if you work out the parentheses, and this will be 4 squared plus 1 squared, so this will be 4 squared plus 1 squared. That will be 17 downstairs, so that will be 40 minus J160, and this will result in the, of course, in the rectangular form will be 2.35 minus J 9.41 in ohms. Okay, this is the expression we required, because I have written this in the rectangular form because I need the addition here, and it will be helpful if I have the rectangular form of ZA. So I can now move on to Z total, or Z of the system. That will be R1. R1 was 8, so 8 plus 2.35 minus J 9.41, which will bring us to the following 10.35 minus J 9.41. If I convert this to the polar rotation, which will result in almost 14, so I will make 14 phase minus 42 degrees, and of course in ohms. Okay, this is now for the impedance. Now once I know the impedance, we already know you can calculate the total supplied current by the voltage source, and using the RMS value of the voltage source, which is of course in this case 70 divided by square root of 2, because it's a pure sinusoidal signal, we can determine the RMS value of the source voltage, source current I mean. The source current of course will result in the current through the R1 and also current through the ZA. And let's move on and calculate the current, total current, of course using RMS value. So I need IS RMS, that will be the VS RMS divided by Z, and VS RMS, root mean square, will be the VS amplitude divided by square root of 2, and that was 70 divided by square root of 2. That's actually the required value, and this is approximately 49.5 volts. And there is of course zero phase orientation for VS. So if I write down VS, the RMS value of that in phasor notation, I will have this amplitude with the phase orientation of 0. So this will bring us to the following. I as RMS will be 49.5 phase 0 degrees divided by the Z, which is 14 phase minus 42 degrees. And this will result in 3.54 phase plus 42 I mean degrees amperes. So we have 3.54 ampere with a phase of 42 degrees. Now, since we know this is the positive phase, the power factor will be a leading. That's actually the situation here. So what is actually the diagram at the moment? So the situation with ZA is the following. We have the voltage source VS, we have the resistor R1, and we have the impedance here, which we called ZA, and this is ground. So if I now denote this point as A, which is exactly the same point actually in the original circuit here, so if I make this also point A, which is exactly the same point, I can now use this circuit to move on with the calculations. Okay, so what I want is, of course, the real power and the reactive power, etc. So let's work through the calculations. For that, I actually need this. For the total reactive power, I look at the 9.41, and for the total real power, I look at actually for this part, so actually the real part. So let's move on. So let's say the following. The P, so let's make a section powers. So P is equal to the IS, of course RMS, squared times the real part of the impedance. And I only take the real part. And for the Q, for the reactive power, I'll again take the source current squared times the imaginary part of the impedance, the total impedance, of course. Okay, and the value of the or the amplitude, I only consider here the amplitudes, not the phases, so this is 3.54, so it is actually 3.54 squared times the real part is 10.35, which is 130 watts. This is actually for P. If I do the same calculation for Q, I will have 3.54 squared times the imaginary part of the Z is 9.41, and that will result in 118 volt amperes reactive. Now this will give actually the expression for S. S is now 130 minus J. I know it is minus because it's a capacitive system, is 180 volt amperes. Now that's actually the station for the apparent power. Let's also express this in the polar notation such that we know the amplitude. It is 176 phase minus 42 degrees volt amperes. As you know, the phase is exactly the same as for the impedance phase, which is not a surprise, of course. We already discussed this. So I know now the amplitudes for the P and the Q. I also know the amplitude for the S, which is 176 volt amperes. Now the final situation is actually the calculation of the power factor. So the power factor, that's the last one, the power factor, which is leading, we already know. So power factor PF, which is the cosine of theta, and which is leading, because the current has a positive phase. This will result in PF, which will be cosine of minus 42 degrees, leading. You have to make this clear. This will result in 0.74 approximately leading. And this will result in approximately 74% leading power factor for this circuit. Okay, this is a little bit complicated circuit because we have a parallel combination and a series combination of 3 components, so that will require also some extra work if you compare this, for example, with example number 2, which we had only one capacitor and one resistor, but the procedure is exactly the same. You follow the procedure of the complete total impedance, you calculate the total current. From that you go to the real power and the imaginary or the reactive power, P and the Q respectively, and from that you determine the expression for S, and for using the polar notation, you know the amplitude of S, and from that, and of course from the phase, well, we already determined actually at the beginning, you can calculate the power factor, and that's actually the whole business for this example. I hope this will clear out the situation again in a little bit more complicated circuit. Of course, we will continue with other examples. So if you want to keep in touch, stay tuned and don't forget to share and like. And thank you very much, and see you next time, and have a nice day.